Okay, here we go. So how about something like this? Now, we want to set up a free body diagram always, right? So the maximum force a grocery stack can withstand and not rip is 334 newtons. The maximum acceleration the sack can withstand then, when 28.6 kilograms are lifted from the floor, is what? Okay. So what are the forces acting on the sack here?
Gravity.
Gravity, so the weight is acting down. And what else?
Normal force.
Well, whatever you want to call it, our lifting force or the pulling force or whatever it's going to be, right? So we've got, here's our free body diagram then. We don't have any horizontal forces, that's kind of convenient. So we'll call that F sub L for our lifting force. And there's mg, right? Okay, what we always do, remember, is we always want to write down what are called the equations of motion. Now, we can finesse our way through these problems in this chapter without always doing this, but we're going to have to do it next chapter every time anyway. So we might as well get into this good habit. We would break down the free body diagram into the horizontal and vertical equations of motion. Now, sometimes, we'll get into some weird situations where maybe they won't always be horizontal and vertical. But we'll deal with that when we get there. They have to be right angle directions though, okay? And usually for us, horizontal and vertical is the clear ticket because gravity acts vertically, right? So our net force in the y direction, because that's really all we have here, is what? Net force means the sum of all of the forces acting on the object, in this case vertically. So are there any positive forces acting on the object? The lifting force. Any negative forces? Yeah, mg, because that's acting down, right? Now, the sum, and there could in some cases in the future be lots of forces acting on an object. We haven't ever had to deal with too many at the same time, but we might get a bunch of them in the future. The sum of all those forces by Newton's second law always equals what? Net force equals ma. When we say F equals ma, that's really what we mean is net force equals ma, right? Okay, so what are we trying to solve for here? We want to know what the maximum acceleration is, right? So can we plug in, well, we got to solve for a, so we'll just divide both sides by m, right? And then we just end up with a by itself equals maximum lifting force minus mg over m. So now we should be able to plug and chug. Okay, so we want the maximum acceleration, so we're going to plug in the maximum lifting force. What is that? What is it? 334 newtons, okay? Minus m, 28.6 kilograms times g. What are the units of g? It's an acceleration, so what would they be?
Meters.
Good. Meters per second squared, good.
I was thinking meters squared.
Yeah. Divided by 28.6 kilograms. And we could have left the units off because we know we're dealing with all normal units, right? Newtons are the standard units of force that we build from MKS units, meters, kilograms, seconds.
So we could have just eliminated the masses, couldn't we?
You can't, because now here's why. This is kind of a math issue. That's a common thing that people want to do, and I can see why. But if we have something like this, like if we have, let's say, 6 minus 2m over m. People want to cancel those masses, but I can't do it because the m on top is not a common factor. It's in a term, right? Now I could do this. If I had 6m minus 2m, then I could write that as m times 6 minus 2, which I could really just make a 4, couldn't I, right? And now I could cancel it because the m is being multiplied on the top by everything, right? Okay, does that make sense? Okay, so what do we get numerically here? Well, first of all, kilograms times meters per second squared just gives us newtons, right? So everything works out the way it's supposed to here. In fact, I hate to say this sometimes, but I really do think when you're learning physics initially, I think it's easier to just not write the units and just be careful with the units. Because I think what happens sometimes is when you add those units, things start to look too complicated. And sometimes people make the mistake of they'll confuse a Newton for a normal force, or they'll confuse a meter M for a mass M or something, right? And so I eventually you might have a physics teacher that tells you differently from that. But as long as you make sure that you're using the right kinds of units, you're not mixing and matching units, it's okay to do. Okay. Having said that, I'm going to erase these. Okay. Okay, so what do we get numerically if we do all this stuff? If we throw that in our calculator.
1.88 was rounded to the third.
Okay, so if we keep 3 sig figs, 1.88. Now we got to pay attention though. What should our units be for acceleration? Meters per second squared. Okay, and that's it. Okay, that's the maximum acceleration we can have. Make sense? Okay. All right. So what else? You tell me. What?
The thing we were ending on yesterday with like 3 parts.
Okay, 3-part one. Yeah, good. Let's do that. So that was like, I think, that guy?
Yeah.
Okay. That's a good one. I like that one. Okay. So you pull a 57.72 kilogram sled across flat, snow-covered ground. The coefficient of static friction between the sled and the ground is 0.313, and the kinetic coefficient of friction is 0.202. Okay, I'm going to change the wording on this first one just very slightly. I'm going to go ahead and change these problems to reflect this change. It's not a big deal, but I think this shouldn't say at least. I think it should say more than. So we need to think about why. I mean, it's not a huge deal, but when we're going to push this sled initially when it's at rest and static friction is acting, I've got to push with a tiny bit more than the threshold to get it moving, right? Does that make sense? Okay. So let's draw our free body diagram. What's this going to look like? What are the forces? You guys help me out here. What are the forces acting on the sled? Somebody tell me one in the direction it's acting. Go ahead, Sean. Normal force is pushing up, so the ground is pushing up on the sled. Good.
Gravity.
Pushes
Down.
down. Okay. How are they related?
They're equal.
They're equal in magnitude, aren't they? Good. Okay. What else?
Friction.
Okay, we got a friction force. I'm going to call it static friction for part A. And a pushing force, maybe. Right, so or a pulling force, whatever. Either way, we'll call it F sub P. Okay? So when we are going to break this thing break it free from the ground, that's going to occur when we just exceed this threshold where the pushing force is at the frictional force, right? So what we're calculating right here, if we set these equal in magnitude, is the threshold force for breaking the sled free. Okay? Okay, so now let's write the equations of motion. Okay, so the vertical equation of motion. The net force, we'll put a y there to remind us it's vertical. The net force is the sum of what forces here? What are the forces acting vertically? So we got, what, is there a positive one? Okay, normal force minus mg, and that's all of them, right? So we have to ask ourselves, is the sled accelerating vertically? No. So what's the net force vertically then? Zero, because net force, by Newton's second law, net force equals ma, and a must be zero, right? So this equals zero. Okay, that's important to us because if I solve for normal force, right, if I just add mg to both sides of this equation mathematically, look what we get. The normal force, which is just the ground's force pushing up on the sled, is exactly equal to the weight of the sled. Okay? That's good. That's going to be useful. Okay, what about horizontally? So horizontally, we've got, looks like we got a pushing or a pulling force in the positive direction and a negative frictional force, right? So the net horizontal force is just pulling force minus static frictional force. And we're going to say that's zero, right? Because we're going to find out what is the threshold there. What's the maximum static frictional force that we have to overcome? So if we solve for pushing force or pulling force, which is what we're really trying to find, isn't it? We just get pulling force equals static frictional force, right? Okay. What's our, we have an equation for that. We have a model for static frictional force. What is that? Okay, mu sub s, good. So pulling force, good. So it's mu sub s times normal force, but what's normal force equal to? Mg. And that's helpful to us because, actually, you know what? Do I have any? I don't this time.
Okay,
Thank you for checking though. So normal force, I can't plug in numbers for normal force directly. I don't know what that is, but I do know what the mass of the sled is, and I know what the acceleration of gravity is, right? So making this substitution is good. That allows me to plug and chug. So then this is just equal to, mu sub s times mg, and that's all stuff I know, right? So my pulling force equals, what is that? Static frictional force is 0.313, 0.313. What are the units of the coefficient of friction? Unitless. Coefficients are unitless, right? So 0.313 times m, which is, what was that, do you remember? 57.72 times 9.80, and so my pulling force is what's that give us? 0.313 times 57.72 times 9.80 is 177.05. So to 3 sig figs, 177, what are the units going to be if it's force? Newtons. There we go. Okay? Make sense? Should we check it? Just make sure. $177 newtons. Oh, I guess I can't. Well, yeah, I'll check them one at a time. How about? Don't do this on the test. Oh, I have to answer all parts. Of course. Okay. Okay, what about part 2? Okay, so now for part 2, let's read the. Okay, so part 2 we want to know a force of at least blank will be required to keep the sled moving at a constant velocity of 1.0 meters per second. Okay, is that 1.0 meters per second? Where's that going to fit into our equations? Nowhere, right? Yeah, it's irrelevant, because as long as we're pulling the sled at constant velocity, the velocity is irrelevant. Our friction model does not depend on velocity, does it? All it depends on is normal force and the coefficient of friction. Okay, so that's kind of just a little extraneous information that I threw in there to just be mean. So this is very similar to the first one, though, isn't it? Right? If we're pulling this thing at constant velocity, what's the acceleration? Once again, if I'm pulling it at constant velocity, what's the acceleration? It's going to be 0, isn't it? Because constant velocity means, what's acceleration? Acceleration is change in velocity over change in time, right? If the velocity is constant, it's not changing, and so the acceleration is 0. Okay, that's something that you'll see that about 1 billion times over the course of the year. You're going to ask yourself that question: is the velocity constant or is it changing? If it's constant, then the acceleration is 0. Okay. So really, this free body diagram that we had up here worked pretty well. The only small change I need to make to any of this stuff is just that that's not static friction anymore. It's now kinetic friction, right? But everything else is the same. Agreed? This is, we're just pulling this thing, and so that the pulling force is exactly equal to the kinetic frictional force, because the MA is 0, right? And so all I have to do to get this answer is just go back and make one little change. Instead of the static coefficient of friction, we want the kinetic coefficient of friction, which is what? 0.202.
And that's all you have to do for the second part?
Yeah, everything else is the same, right? You see that? Because wouldn't you agree that that vertically nothing has changed, right? So we still know that the normal force equals mg. Horizontally, pulling force is equal to frictional force, right? And so what do we get when we plug that in? Let's see. Come on now, where's my, there. So let's go back up to this calculation, and let's just, if I hit second left, it scoots me all the way over. You know that trick? And then we get 202, enter. So 114. Okay. Oops. Okay. 114. And then now let's look at part 3. Okay, what about part 3? So part 3, now a force of blank must be applied to the sled to accelerate it at 2.84 meters per second squared. Okay, so now my free body diagram is changing a little bit. What do I have to change about it?
The pulling force is longer than the force.
Okay, good. Now we are going to have a net force, aren't we? Because we are going to have some acceleration, right? So there has to be an unbalanced force acting there, right? So this guy is going to be a longer vector, okay? And this is no longer equal to 0. It's now equal to what? The net force, MA. Good. And I'm really just trying to solve for F sub P, aren't I? So I'm going to go ahead and erase some stuff here. Okay, and I'll change colors so we can see there's a difference here. Okay, so then if I want to solve for F sub P, this is the equation of motion that I'm using. So to isolate F sub P, what's the only thing I have to do? Yeah, just add the friction to the other side of the equation, right? So I get pulling force just equals friction plus MA, and that's kinetic friction, I guess, isn't it? Now don't lose sight. Sometimes the physics gods are giving you little hints about the way things work when you do the algebra in physics situations. Think what this means. When we want to now accelerate this sled, the pulling force is doing two things, isn't it? And these are the two parts that the pulling force is satisfying. It is overcoming friction, like we did in part 2, but then we're adding another increment to the pulling force to cause some net acceleration. Does that make sense? So really, that, if you think about it and stare at that equation for a little bit, it kind of makes sense that it is the way it is. All we have to do now is plug in our stuff. We know that the kinetic frictional force is just what we had right there, isn't it? Right? It's just, this is equal to mu sub k times mg, right? Just like before, plus ma. And so what's that going to give us? 0.202 times 57.72 times 9.80. So I could have just used that stuff, couldn't I? Plus 57.72 times 2.84. 2.84. And so my answer is really just going to be the same thing I got before, right? Because that's the calculation resulting from the frictional force, plus 57.72 times 9.8. Oops. No, times 2.84. Sorry. Right, not times 9.8. So 278 newtons is what I get from all this stuff. For part 3. So let's try them out. See how we did. This would be kind of embarrassing if it didn't work, huh? So what do we got? 114, 278. All right. Got it. Okay. Make sense? What else do you want to look at? What's that? Like these kind right here? Yeah. Okay. Oh yeah, these are the instruments in the balloon. These would be good ones. Oh, look at these. In fact, I'll tell you what a really good one is. This is the granddaddy of them all right there. That's a pretty hard problem. Right? Should we look at this one? Okay. This is pretty cool, though, that we can solve this problem, if you think about it. I mean, this is big time stuff. Okay, so let's take a second here and talk about this. So what's going on? The instruments attached to a weather balloon have a mass of 4.88 kilograms. The balloon is released and it exerts an upward force on the instruments of 103 newtons. So what's going to happen then? What's going to happen to the instruments, presumably? Yeah, they're going to accelerate upward, aren't they? Okay, after the balloon has accelerated for 9.24 seconds, the instruments are released. So imagine that we just cut the string or something somehow, right? The instruments will not have a downward velocity until a time of at least blank has passed since the balloon was first launched. Okay? Now, that's an awkward way of stating this maybe, but I took this from a physics book. I can't remember, this might have been our book, I can't remember which one. The instruments will not have a downward velocity until a time of at least blank. Well, what's going to be the threshold for when the instruments begin having a downward velocity? Okay, so when they get snipped, from the balloon, they're traveling up, right? And so as soon as they get snipped, do they immediately start down? No, what are they gonna do? Okay, good, they're gonna coast upward a little bit maybe, right? And then, so now, I ask again, what's gonna be the threshold for when they start to move down?
When their speed reaches zero.
Okay, when the velocity reaches zero, right? That's gonna be the highest they get, and every time after that, they're gonna be moving downward, correct? Okay, gentlemen.
We had a couple questions about a few of your freshman students.
Oh, okay,
Is it?
what do we got? Here, hang on. It's gotta be quick though.
Okay. Sweet. So just, yeah.
Okay, so, yeah, it's gonna, so that's really what we're looking for then, right? Is how long is it gonna take for this thing to reach its highest point? Now, is anything gonna make this problem a little more complicated? How many parts is it gonna have? Okay, now, maybe I can clarify something for you here. Why do we have to have multiple parts? Well, okay, it's not even the up and down part, because like if I was gonna throw a ball up in the air, as soon as it leaves my hand, all the way until it comes back to my hand, that's one part. Because the acceleration stays the same the whole time. The force on the ball is the same, right? What forces you to have different parts to a physics problem is when the net force changes, which is the same thing as saying when the acceleration changes, okay? So does the acceleration change here? It does, doesn't it? It changes from a positive acceleration caused by the balloon to a negative acceleration caused by the weight, right? So how many parts am I gonna need? 2. Yeah, you need 2 parts. Good. And so really this just honestly becomes kind of a kinematics problem in part 2, doesn't it? In part 2, once the instruments are cut free from the balloon, what's the only force acting on the instruments? Gravity. And if the only force acting on them is their weight, well, we don't even need to turn that into a mechanics problem. What's the acceleration gonna be? Yeah, negative 9.8, right? And so this just is a kinematics problem in part 2, isn't it? Okay, but in part 2, before we even jump into the other stuff, in part 2, okay, so once it's in free fall, right? What are we trying to find? Well, I guess time, right? So we want to find the time from part 2, and probably the time from part 1, which we already know. Just add those together for our final answer, right? Because it wants to know how long after its first launch does it take to get to its highest point, right? So that's what we're trying to find. What are we given, or presumably can we find from part 1 that we can add to this list of kinematic quantities for part 2? Okay, so the initial velocity for part 2, where do we get that? Yeah, the final velocity from part 1. Good. And then what's our final velocity going to be? You already told me. 0. And then what's probably the only other thing we need?
Acceleration?
Yeah, and what's the acceleration? Very good, okay. And so we can use a pretty simple equation then to solve for t, can't we? Right, but we gotta get that v naught. Okay, well the v naught comes from part 1, and that's actually probably the harder part, right? So if we go back to part 1, what's our free body diagram look like? Pretty simple. What are the forces acting on the instruments? Okay, gravity down, good. And what do you want to call it? I don't know, like buoyant force upward? Because that's really what it is a buoyant force from the balloon. So we'll just call it F sub B, call it tension if you want, I mean, whatever you want to call it, but we'll just call it F sub B. So then, what's our equation of motion? We don't have any horizontal forces, right? So our net force acting vertically, so we'll put a Y there, is a sum of what forces then? So what forces combine to give us the net force? Okay, buoyant force minus mg, and what's that going to be equal to? ma, because there is acceleration, isn't there? Okay, Okay, so there's our equation of motion. Now, really what we're just trying to do here for part A probably is calculate, we want to turn it into a kinematics problem too. If we had the acceleration, that would be helpful, wouldn't it? But we can solve for A, can't we? Just divide both sides by M. And A is going to give us all this stuff on the left over M. We can calculate that, right? So what is that? If we plug and chug here, then that's going to give us, what's the buoyant force? 103, good. Minus, what, 4.88 times 9.8 divided by 4.88, right? So that's going to give us some acceleration that we can fill in. What else do we know from part A? We know time. Good. Time is 9.24 seconds. What's our initial velocity? 0. And our final velocity is what we're really trying to find, isn't it? Okay, so let's calculate acceleration. So that's going to give us, let's see, that's going to give us 103 minus 4.88 times 9.8 all divided by 4.88, which is, to 3 places is 11.3. I'll keep it in my calculator to more places though, how about? Okay. And so then I can calculate V. What's going to be the equation I'm going to use to calculate V there? Yeah, good. So V equals V naught plus AT, that's 0. So I just get 11.3 with more sig figs times 9.24, which is what? Somebody have a calculator there that can tell me? What is it again? 104, okay. 104-ish meters per second. And so that's what goes up here. And then I'm just doing the same equation, aren't I? Right, I just want to solve for t this time. So we know V equals V naught plus AT. If we go to part 2, V is 0. So what are the 2 steps to solve for t? Good, subtract V naught, divide by A. So t equals negative V naught over A. Okay. So let's do some calculations then. So we get, what do we get here? So, okay, so here's our acceleration times 9.24 gives us our 104 rounded. But here's our unrounded final velocity, right? Which becomes our initial velocity over here. And so what do we have to do? We have to multiply that by -1. Probably could have skipped that. Divided by our acceleration of -9.8 gives us 10.66, et cetera, et cetera. So that's our time. We want the total elapsed time. So I'm going to add to that the 9.24 from the first part. Everybody agree? Wow, that seems like a pretty big. Yes, that's right, huh? Okay, so plus 9.24 is 19.9000. So rounded to 3 places, 19.9. Okay. Should we try it?
Yeah.
What are my units going to be? Seconds. Got it. How about that? Pretty good stuff, huh? What do you know? Is that helping? Good.